Okay, so here's my solution to the first problem. This disc is 100 kilograms. The block is pretty heavy. It has a mass of 75 kilograms, and the pulley has 10 kilograms. And so we're going to have to take into account the disc. I assumed it was going downhill because it was heavier than the block. So the disc is rolling downhill and moving. So it's rotating and moving. The pulley is only rotating, and the block is only translating. So it's a nice review problem. The block is only translation, the pulley is only rotation, and the disc has both. Okay, so whenever you have this type of problem with a rolling wheel, a rolling disc, a rolling ring, or something like that, one of two things can happen. Either that disc is rolling without slipping, or it's slipping while it's rolling, so sliding while it's rolling down. This has implications on what you assume. So I'm going to assume that this is rolling without slipping. The next problem will be a sliding problem with rolling, so you get to see both. So in this problem, I am assuming that the disc is rolling without slipping, and that means that this friction force here is not mu times n. It's less than mu times n, so it's unknown. It ends up being an unknown variable. But the added information we get, knowing that it's rolling without slipping, is that later on when we do the kinematics, we'll see that this acceleration of the disk is just going to be r times alpha because this bottom point here is a point of zero acceleration and zero velocity because it's not slipping. So we'll get to that later. Let's continue on. So you can see I'm going to draw three free body diagrams, one for the disc, one for the pulley, and one for the block. And so here's the free body diagram for the disc. I have that unknown friction I just highlighted in yellow there, the normal force, the weight pointing vertically down due to gravity, and the tension in that string there. And that's going to equal MA going down the hill. It's not hopping off of that incline, so the acceleration is going downwards at 30 degrees, angled at 30 degrees downward, I thought. It turns out it's actually moving uphill. And therefore, if it's going down, the wheel must be spinning counterclockwise, and I've drawn I alpha correspondingly there. So the second free body diagram is of the pulley. And so now, when the pulley has mass, in all the problems up until now, when the pulley doesn't have mass, the tension on the two sides are equal. So this is a key feature of a problem with pulley with masses, pulleys that have mass. The tension on the two sides of the pulley are different because there's some inertial resistance to rotation from the mass of the pulley. So that will equal I alpha on the right-hand side. There's no MA because it's pinned down, it's not moving. And so finally, the third free body diagram is the simplest. That block has a tension going up. That's T2, which is not the same as T1 as we discussed earlier, and the weight going down. And I assumed incorrectly that the wheel was rolling downhill, which meant the block was going upwards, and I have MA pointing up on the right-hand side. So note that these two tensions are equal, and these two tensions are equal because they're the same segment of rope. However, these two are not equal because of, as we discussed earlier, the mass of the pulley. Okay, so all we need to do is go through these free body diagrams and get equations. Quickly, just looking at it, it looks like I'll take the y components of the block. I'll take moments about the center of the pulley so that I don't involve those Rx and Ry reactions. And that disk will do three equations, x, y, and moment. So I'm taking the path of least resistance. So I'm starting with the block. That's the easiest one. So I'm taking sum Fy up as positive, so T2 up minus the weight going down will equal MA, which I assume going up. we'll get a negative sign, as you see in a little bit for A. It's actually going down. Okay, in the pulley, it made sense to me to take moments about the center of the pulley. That way, the reaction X and Y at the center doesn't come into the equation. So taking moments about the middle, the radius was 0.2 meters, and counterclockwise is positive when I take the moments. So I have T1 at a moment arm of 0.2, that's positive, going counterclockwise. T2 with a moment arm of 0.2 again, it's going clockwise, so I put negative T2 times 0.2, and on the right hand side I just have I times alpha of the pulley. Okay, so the disk, we now have three equations, and I've been learning whenever you have an incline problem, it's probably best to take your components along the direction of the incline. So and also because I thought the disk was rolling downhill, I made X positive going downhill. So if you look up here near the picture of the free body diagram, I've drawn in what I've considered positive X and positive Y. And because normally we think of X as horizontal and Y as vertical, I said X prime and Y prime to show that these are the rotated 30 degrees axes. Okay, so I'm now going to take the components in the Y prime direction. I'm taking, as shown in that picture, up and to the left is positive. And so all you do is you go to the picture and look for anything in that direction. So the normal force is going up and to the left, positive. The weight has a component in that Y prime direction of WD cosine 30 degrees, and it's going down and to the right, so negative. On the right-hand side, there are no accelerations in the Y prime direction because the disk is rolling down the hill. It's not hopping up off of the ground, so that is 0. We could probably just solve that one right away, and is the weight times cosine 30 degrees, but I'll wait till later. Okay, so now we'll do X component, positive going downhill again because I thought the disk was rolling downhill. So there's a component of the weight going downhill of WD sine 30, and again, I said downhill is positive. The tension is going uphill, so that's negative, and the friction is pointing uphill, so that's negative. And that will equal mass times acceleration, which I incorrectly assumed was pointing downhill. So finally, we need to take the moments somewhere. Okay, and so one way is to take the moments about the center of the wheel, but then you're going to get this friction force has a moment. So I thought, if you look at the free body diagram, I thought taking a moment about this point right here, where the normal and the friction forces meet, I thought that would be a good idea because then those two forces are eliminated from the moment equation. But that meant that I was going to have to take the moment of this weight about the origin. So an easier way to do that than trying to find some kind of distance, perpendicular, cross product, is I just took the weight and I broke it down into its Y and X components. And I noticed that the Y component is pointing straight through O. So the moment due to the weight is just the X prime component times the radius. That's the moment around O. So that, in fact, is what I did. So that's WD times sine 30 is the X prime component of the weight. It has a moment arm of 0.4, and it's going counterclockwise about O, so it's positive. The rope has a tension 1, and its moment arm is the diameter, which is 0.8, and that's going counterclockwise, so negative. On the right-hand side, taking moments about the bottom, you have the mass times acceleration with a moment arm of a radius of 0.4, and you also just have the I alpha as a moment. Okay, so we have 5 equations here. What we need to do is put in the values for the mass and the moment of inertia. I'm going to skip that. I just wrote it out right here. You were given these masses, and I think it said the pulley. Let's see, the pulley can be considered a thin disc, and they even called that wheel a disc. So if you look back to the moment of inertia thing, here we go. Polar moment of inertia is 1/2 mr squared. So this was just 1/2 mr squared, 1/2 mr squared. Okay, to be honest, I didn't actually look at that sheet. I have memorized these three. Circle. I is 1/2 mr squared. Skinny bar. About the middle. I is 1/12 mr squared. And I can remember that because it looks like the one for a rectangle in moment mechanics of material, 1/12 base tensile cube, and the bar kind of looks like a rectangle. Okay, and then the last one is if you have some weird shape and they give you the radius of gyration. In this book, it's K for radius, so think radius of gyration. I is just mass times the radius of gyration squared. Okay, with no 1/2, 1/12 or anything. Those are the three I remember, and those get me through almost all of the problems. Okay, so let's continue. So I rewrote the 5 equations there with the numbers put in for I and M. Okay, so we have 5 equations, but this one is done already. Okay, so we don't need that equation. We know that the normal force is 850 newtons. So really, we have 4 equations, and then if you count the unknowns, there's T1, T2, that friction force, and then 4 acceleration type things. Acceleration of the block, alpha of the pulley, acceleration of the disc, and alpha of the desk. That's not going to work. 7 unknowns with 4 equations. You need only 4 unknowns. That means we need to get rid of 3 of the unknowns. So whenever you have too many unknowns, like in energy, you only have 1 equation. So if you have more than 1 unknown, it's too many. Kinematics is always the answer and comes to the rescue. So this, unfortunately, just involves you thinking about things and knowing like R alpha, R omega, and those sorts of things. Okay, so let's put on our thinking cap and think about this. Okay, so what we have here, let me pick a different color since I've already drawn this thing in red. So now all my markups are going to be in blue. We know this block is going up at acceleration of b. Actually, it's going down because I guessed wrong, but I thought it was going up with acceleration of b, acceleration of block. The string, even though the tensions are different on both sides, the string, everything has the same displacement, same velocity, and same acceleration. So that means this point of the string right here on the pulley also has an acceleration of a block, and this point at the very top of the disc has an acceleration of a block. So the other thing we're going to use is we know that if you can find the spot that's not moving and you measure your radius from there, we know that the acceleration will be r times alpha because it's just spinning about that point. So where are the points that are not moving? So the pulley is definitely pivoting about the center. Now, because I assume no slip, we have to check that later, this wheel is spinning about the bottom where it's touching the ground. So, you know what? To make it more apparent, I'm going to draw a little pin there. So, there you go. That wheel is spinning about there, and that disc is spinning about the bottom, not about its center. Okay, so now we know that r times alpha will be the acceleration. Okay, so we can now do some things. We know that the tip of that wheel, the pulley, is going at AB. And so it'll be a radius of 0.2 times alpha of the pulley will equal A of the block. And so what I decided was I'm going to make everything in terms of A block, and I'll get rid of 3 unknowns. So solving that for alpha of the pulley, you get alpha of the pulley is A block over 0.2 or 5 A block. Okay, same thing for the disc. We know the top of the disc has an acceleration where the rope touches of A block. The distance from the pin, which is at the bottom of the wheel, disc, to that block is the diameter. So it's 0.8, and then 0.8 times alpha of the disc will equal A block. And again, solving for alpha of the disc, you get 1.25 A block. Okay, we also want to get acceleration of the disc in terms of acceleration of the block. So we know that the acceleration of the disc is its distance from the pin, which is 0.4, the radius, times alpha the disk. Well, we just solved alpha of disk in terms of A of the block, 1.25 A block. Put that in there and you multiply it all out and you get half of the A block. Now, this makes sense because it's like this, right? If your acceleration is proportional to your distance from the pin, which is at the bottom, the middle of the disk is half the distance away as the top of the disk, so that's half the acceleration, so that makes sense. Okay, so then what I did was I took our 4 equations, and everywhere there was an alpha pulley, alpha disk, or A disk, I put in the equivalent expression in terms of A block, and this is what I got. And then I got lazy. I just have a thing on my calculator where I could put those 4 equations into it, and then I solved and I got these things, and then I found out that the acceleration of the block was 4.17 meters per second. I got a negative, which means the block is going down, and then I put in acceleration of the disk is half of that, so 2.09, again negative, meaning going up. So the last thing we have to do is check if it's slipping or not. So one of the things you solve for when I solved those 4 equations was I was able to get the friction force is 297 newtons. Is that less than the static coefficient times, or the kinematic, static coefficient of friction times the normal? So there's FF. Mu was 0.4, and way at the top we got the normal force was 850 newtons. You multiply that out, you get 340, which is greater than 297, so yes, it is not slipping. Otherwise, we'd have to start all over, and I don't want to do that. Now, this next problem is slipping, but to illustrate how the process works, I'm going to assume it's not slipping, find out I'm wrong, and then redo it.